Hello everyone. In this video we are going to discuss Atwood's machine, and in this particular case I am going to take a pulley with mass. So we are going to approach this problem using Lagrangian mechanics. So in Lagrangian mechanics we know we have to first write the Lagrangian of the system. Lagrangian of the system L is equal to T minus V, where T is the kinetic energy of the system and V is the potential energy of the system. First, let us write the kinetic energy. So T will be equal to, there are three objects. First block's kinetic energy half m m1 v1 square plus second block's kinetic energy half m2 v2 square plus the rotational kinetic energy of the pulley, that will be equal to half I omega square. Now let us assume that the pulley is a disk of mass capital M and radius capital R. Okay, so we know the moment of inertia, that it will be mr square by 2. Let it be there. Now let us see the constraint relation. Because the length of the string is fixed and the string is unstretchable, if m1 is moving with velocity v1 in the downward direction, then m2 will be going up with velocity v2. Similarly, if m1 is having acceleration a1 in the downward direction, m2 will be going up with an acceleration a2. Now, because the length of the strings are fixed, whatever speed m1 is coming down, m2 should be going up in the opposite direction with the same speed. And the same is applicable for acceleration. So we can write v1 will be equal to minus v2 and a1 will be equal to minus a2. So let us use this idea and rewrite the kinetic energy equation. So kinetic energy T will be equal to half m1 v1 square plus half m2. Now v2 is minus v1, but because we are taking the square, I can still write v1 square plus half moment of inertia of a disk is mr square into omega square. So this is the kinetic energy. Now, because we are using the Lagrangian mechanics for this problem, we have to consider a generalized coordinate. So here, because there are two masses and a pulley, the best way to choose a generalized coordinate is to take the distance of mass m1 from the center of pulley and let it be x. Then the distance to the mass m2 will be L minus x. Okay, why it is L minus x? Because we know length of the string is fixed. So if one side it is x, the other side will be a constant minus x. Okay, so that means kinetic energy, in the equation of kinetic energy, we can see that v1 will be equal to x dot and v2 will be equal to minus x dot, because the derivative of L minus x will be minus x dot, as L is a constant. Now what about the omega? So we know omega is the angular velocity of the pulley, and because the pulley is rotating, and if we assume that the rope or the string is not sliding over the pulley, then the rotation of the pulley along with the string will be a rotation without slipping or sliding. So that means whatever is the speed of the string, that will be the same for the circumference of the pulley. So that means v1 or v will be equal to r omega. So that means x dot is equal to r omega. So we can make the substitution in the kinetic energy equation. Then the equation for kinetic energy will be T is equal to half. Now because v1 square is common, I can take that outside. Half m1 plus m2 v1 square, that is x dot square, plus half moment of inertia mr square into x dot square. So sorry, omega square. So what is omega? Omega is x dot by r. You can see from here omega is equal to x dot by r. So omega square will be x dot square divided by r square. So here r square cancels. So kinetic energy expression reduces to half m1 plus m2 plus capital M into x dot square. So here in the when I substituted for the moment of inertia of the disk, I have made a small mistake. Moment of inertia of a disk is mr square by 2. So that by 2 I forgot to write. So here the capital M will be having a denominator 2. Now what about the potential energy of the system? So to measure potential energy, we have to have a reference. So we will take the level of the center of mass of the pulley to be our reference point. So with respect to that reference, m1 is at a distance at a depth x down and m2 is at a depth l minus x. So potential energy V will be equal to, because the masses are below the reference point, minus m1gx potential energy of the first block, then potential energy of the second block will be minus m2g into l minus x. Now what about the pulley? Because the center of mass of the pulley is the reference, the potential energy of the pulley itself will be 0. So we got the kinetic energy and potential energy in terms of our generalized coordinate x. Now let us write the Lagrangian of the system. L is equal to T minus V. So that will be equal to half m1 plus m2 plus capital M by 2 x dot square minus potential energy, that will become plus m1g x plus m2g l minus x. So we got the Lagrangian of the system. Now to get the equation of motion of the system, we have to write the Lagrangian equations. So that is d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. There will be only one equation of motion because there is only one generalized coordinate. So let us find each term and substitute in the equation. So first dou L by dou x dot, that will be equal to half m1 plus m2 plus capital M by 2. Derivative of x dot square with respect to x dot will be 2x dot. So 2 cancels. Similarly, dou L by dou x will be, you can see in the from the equation, m1g minus m2g. The derivative of L is 0 because it is a constant. Now let us substitute these things into the Lagrange's equation of motion. So we will get d by dt of m1 plus m2 plus m by 2 x dot minus m1g plus m2g is equal to 0. Now when we take the time derivative, we will get m1 plus m2 plus capital M by 2 x double dot will be equal to m2 minus m1, sorry, m1 minus m2 into g. So x double dot will be equal to m1 minus m2 divided by m1 plus m2 plus capital M by 2 into g. So here x double dot is the acceleration of the system. Okay, so for an Atwood's machine with a pulley with mass, we found the acceleration of the system. So here the assumptions are the string is a massless string, but it is an inextensible string, so the length is constant. And also we have assumed that the motion of the rope or the string around the pulley is motion without slipping. And also we have assumed that the pulley is a disk of mass m and radius r. I hope you understood the idea. Thank you.